Hi, hello. My name is Dr. C.H. Suresh Kumar, working as a lecturer in mathematics at TRR Government Degree College, Khandapur, Prakasam District. In this session, we learn about the topic, namely vector subspaces. In the previous session, we are all learn about what are the properties of vector spaces. Definition of vector subspace. Let Vf be a vector space and W be a non-empty subset of V. That is, W is a subset of V. This means all the elements of W are belongs to V. If W itself a vector space over F with respect to the same operations defined on V, then W is called a subspace of V. Note, we are all know what are the operations. The operations are, one is vector addition and the second one is scalar multiplication. If W is a subspace of V, then W is a subgroup of V. That is, W plus is a subgroup. Since V subset of V, hence V is also a subspace of V. Similarly, the set with the 0 vector is also subset of V. It is also a subspace of V. This subspace is called a 0 subspace or null space. These two subspaces, what are they? V and 0 vector set. These two subspaces are called improper or trivial subspace of V, and the remaining subspaces except V and 0 vector set, the remaining subspaces are called proper or non-trivial subspace of V. Let us take a theorem. It is an important theorem. This theorem tells about the necessary and sufficient condition for a non-empty subset W of a vector space V to be a subspace of V. The necessary and sufficient conditions are two. One is alpha beta belongs to W implies alpha minus beta belongs to W. This is one. And the second one is A belongs to F and alpha belongs to W implies A alpha belongs to W. These two are the necessary and sufficient condition for a non-empty set W of a vector space V to be a subspace. Now, proof. Necessary condition. In this, assume that W is a subspace of V. We prove the two conditions in the above theorem. What are they? One is alpha minus beta belongs to W and the other is E alpha belongs to W. 1. Since W is a subspace, by the definition of subspace, W itself a vector space, and also W plus is a subgroup of V. Since W plus is a subgroup, so if alpha beta belongs to W, then alpha minus beta belongs to W holds. Next, second one. Since W is a subspace of V, we know the definition of vector space. Since W itself a vector space, from the definition of vector space, the second property tells that W is closed under scalar multiplication. That is, A belongs to F and alpha belongs to W implies A alpha belongs to W. So we prove the given two conditions. Right now, sufficient condition. In this, let W be a non-empty subset of V, satisfying the given two conditions. Now we prove W is a subspace of V. That is, W is a vector space itself. For that, we are verifying the properties of vector space conditions. In one, we have to prove W plus is an abelian group. So, in the definition of abelian group, we have to prove 5 laws. One is closure law, associative law, identity law, inverse law, and finally commutative law. For that, first one, identity law. Alpha belongs to alpha belongs to alpha. By using the condition 1, alpha minus alpha belongs to W. That is, 0 bar belongs to W. So, the 0 bar, that is 0 vector, is also the 0 vector in W. So, 0 vector is the identity element in W. So, W has one identity element. And the second one is inverse law. In this, we have to prove for each element in W has additive inverse. If 0 bar belongs to alpha W and alpha belongs to W, implies by using the first condition, we may write 0 bar minus alpha belongs to W, implies minus alpha belongs to W. Here minus alpha is the additive inverse of alpha. That is 2. Now 3, closure law. Again take alpha beta belongs to W. Since by 2 inverse law beta belongs to W, implies minus beta also belongs to W. From the first condition, alpha minus beta belongs to W, implies alpha plus beta belongs to W. This is closure law. So, W is closed under vector addition. Now, fourth law, associative law. Since all the elements of W are belongs to V, that is W is subset of V, so thereby vector addition in W will be associative. Next, fifth one, commutative law. Similarly, in the above, since W is subset of V, all the elements of W are also the elements of V, thereby vector addition in W will be commutative. From these five laws, we conclude that W plus is an abelian group. And the second property we have to prove W is closed under scalar multiplication. From the condition 2, namely A belongs to F and alpha belongs to W implies A alpha belongs to W. From this condition 2, this implies W is closed under scalar multiplication. Now, third property. Since W is subset of V, hence these four laws holds. One is A into alpha plus beta equal to A alpha plus A beta. A plus B into alpha equal to A alpha plus B alpha. A into B alpha equal to AB into alpha. 1 into alpha equal to alpha. From these three properties, we conclude that W itself a vector space under the operations on V. Hence, W is a subspace of V. This is theorem we complete very well. Let us go to another theorem. This is also the necessary and sufficient condition for a non-empty subset W of a vector space V to be a subspace. The condition is now only one, that is A comma B belongs to F and alpha beta belongs to W implies A alpha plus B beta belongs to W. Necessary condition. Assume that W is a subspace of V. Let A comma B belongs to F and alpha beta belongs to W. We had to prove that A alpha plus B beta belongs to W. Since AB belongs to F and alpha beta belongs to W, so A belongs to F and alpha belongs to W. Since W is a subspace, W is a vector space, then the definition of vector space, we know that the second property tells about A alpha, W is closed under scalar multiplication. Hence, A alpha belongs to W. Similarly, B belongs to F and beta belongs to W. This implies from the definition of vector space, W is closed under scalar multiplication. B beta belongs to W. We get two types. One is A alpha belongs to W. A alpha belongs to W and B beta belongs to W. Since W is a subspace, W is a vector space. Hence, W plus is an abelian group. From the closure property, we take A alpha plus B beta belongs to W. Hence, we prove the required condition. Let us move sufficient condition. In this condition, in this case, we assume that the condition, given condition, holds. That is, AB belongs to F, alpha beta belongs to W implies A alpha plus B beta belongs to W. Now we have to show that W is a subspace of V. That is, W is a vector space. for that in one we had to prove W plus is an abelian group. That is closure law, associative law, identity law, inverse law, commutative law. These 5 laws must be wholes. 1. Closure law. 1 belongs to F and alpha beta belongs to W. From the given condition, 1 alpha plus 1 beta belongs to W. That is, alpha plus beta belongs to W. So W is closed with respect to vector addition. Now, 2. Associative law. Since W subset of V, that is, all the elements of W are in V, so W is associative with respect to vector addition. Third, identity law. If we take 0 and 0 belongs to F and alpha beta belongs to W, then by the given condition 0 alpha plus 0 beta belongs to W. 0 alpha plus 0 beta belongs to W. That is 0 bar plus 0 bar belongs to W. So 0 bar belongs to W. So there exists an identity element in W. What is that identity element? That is 0 vector. Inverse law. That is, we have to prove each element in W has additive inverse in W. If we take -1 and 0 belongs to F and alpha beta belongs to W, from the given condition we may write -1 alpha plus 0 beta belongs to W. That is minus alpha plus 0 bar belongs to W. That is minus alpha belongs to W. So here minus alpha is the additive inverse of alpha in W. Next, commutative law. Since W subset of V, we have if alpha beta belongs to W, then alpha plus beta equal to beta plus alpha. This is commutative property. Then we call W is commutative with respect to vector addition. From these 5 properties, we conclude that W plus is an abelian group. The second property, we had verified the second property. What is that? That is W is closed under scalar multiplication. If we take A0 belongs to F, alpha beta belongs to W, by using the given condition A alpha plus 0 beta belongs to W, that is A alpha plus 0 bar belongs to W, so A alpha belongs to W. Hence W is closed under scalar multiplication. And the last one, the third property, since W subset of V, all the elements of W are the elements of V, the 4 properties holds. One is A into alpha plus beta equal to A alpha plus A beta. A plus B into alpha equal to A alpha plus B alpha. A into B alpha equal to AB into alpha. 1 into alpha equal to alpha. These four properties holds since W is subset of V. From these 1, 2, 3, we have W is a vector space, hence W is a subspace of V. These two theorems plays an important role for the verification of a subspace. Okay, thank you one and all.